Inside an early steam workshop, a perfectly good engine could be disabled by one missing nut because the next workshop's nut might not fit its bolt. Imagine a locomotive stopped beside the track because one nut has vanished. The mechanic has spare nuts. He has iron, files, taps, dies, and skill. Yet none of the replacements will turn onto the exposed bolt. The diameter looks right, but the spiral climbs at the wrong rate, or its groove meets the ridge at a different angle. In the early industrial workshop, that was not absurd. A screw belonged to a local language. Another maker's thread could be incomprehensible. The small hinge that helped machinery escape this world was a geometric choice published in 1841, 55 degrees. A screw thread appears obvious only after generations of standardization. Wrap an inclined plane around a cylinder and rotation becomes forward motion. But making two separately produced pieces demands agreement. They must share diameter, pitch, profile, depth, and sufficient precision. Before an accepted system, workshops developed their own practices. The Science Museum Group summarizes the problem directly: each machine shop used a special thread of its own. A nut and bolt could be engineered as a pair, but a broken part might have to be copied for that particular machine. This mattered more as the Industrial Revolution connected machines to other machines. A village smith could adapt a one-off hinge. A railway company operating locomotives, pumps, signals, and depots across hundreds of miles needed parts that traveled without their original fitter. Production was becoming distributed. Repair was becoming urgent. The obstacle was not ignorance of screws, screw-cutting lathes and workshop gauges already existed. The obstacle was coordination. Every maker could produce a good thread while the larger system still produced incompatibility. Joseph Whitworth approached that coordination problem as a toolmaker. Born in Stockport in 1803, he trained in the workshops of leading mechanical engineers before establishing his own Manchester business. Precision was his commercial language. His contribution was not merely to invent a handsome spiral and demand obedience. He collected examples from important British workshops and measured existing practice. A later U.S. National Bureau of Standards circular explains that the chosen angles, diameters, and pitches represented averages of engineering practice. Whitworth turned workshop custom into a common proposal. In 1841 he presented on an uniform system of screw threads to the Institution of Civil Engineers. The paper's premise was brutally practical: diversity created expense and delay, while a constant thread for a given diameter would remove the evil. His system assigned standard pitches to diameters and used a thread profile with an included angle of 55 degrees. Crest and root were rounded. The rounded form reduced vulnerable sharp edges and could be reproduced with matching tools and gauges. The exact shape was less important than the fact that makers could agree to make it again. Whitworth did not possess a modern standards agency capable of commanding adoption. His proposal spread because it solved expensive problems and because his firm sold accurate equipment for making and checking it. The Institution of Mechanical Engineers says the system began in 1841 and was universally accepted in Britain by the 1860s. Science Museum collections preserve Whitworth taps, dies, wrenches, and screw plates from the 1850s, physical tools that converted a published rule into metal parts. A standard without gauges would have remained an essay. Gauges made conformity visible. The new system altered the meaning of a spare part. Under local threading, a spare was often spare for one machine. Under common threading, a nut of stated size could be manufactured elsewhere and still have a reasonable expectation of fitting. The change did not instantly create complete interchangeability. Dimensions, tolerances, bolt heads, materials, and many other features also required control. But thread compatibility removed one pervasive source of friction. It separated the identity of a fastener from the identity of the workshop that made it. Railways offered ideal pressure for adoption. They combined large capital equipment with vibration, wear, weather, tight schedules, and geographically scattered maintenance. The Science Museum notes that Whitworth's national specification became generally accepted, while the Institution of Mechanical Engineers places its rise in the railway era's demand for machine tools. A common screw reduced the number of private dialects maintenance crews had to understand. Had every railway guarded its own thread indefinitely, repair depots would have needed more inventories, more custom tooling, and more time whenever machines crossed organizational boundaries. A striking recent discovery shows the standard moving into architecture. The Crystal Palace for the Great Exhibition of 1851 had to be assembled at unprecedented speed from repeated components. Research published in 2024 measured surviving bolts associated with the palace sites and Isambard Kingdom Brunel's South Water Tower at Sydenham. The researchers found evidence consistent with Whitworth's system, including a surviving nut that fit a newly cut 7/8-inch Whitworth bolt. They argue that tens of thousands of interchangeable fasteners helped make rapid construction possible. That claim deserves careful wording. Not every surviving Crystal Palace bolt follows Whitworth perfectly, and the article distinguishes measurements and inferences. The important point is not that one man personally held the glass house together. It is that builders were already exploiting standardized thread forms barely a decade after the paper. A building famous for modular iron and glass also depended on less visible modularity inside its joints. Spectators saw a palace assembled like the future. The future worked partly because nuts no longer had to remember which bench had made them. Whitworth displayed another expression of precision at the Great Exhibition, a measuring comparator. He claimed sensitivity to a millionth of an inch. The Science Museum now cautions that this claim was exaggerated because temperature changes would overwhelm such performance, and National Physical Laboratory testing did not support it. That correction matters. The story is not a Victorian genius myth in which every boast becomes fact. Whitworth's durable achievement was institutional and practical. He made accurate tools available and persuaded industries that common dimensions were valuable. Britain's standard did not become the final universal thread. In 1864, American engineer William Sellers proposed a system with a 60-degree profile and flattened crests and roots, easier for ordinary machinists to cut. The American Society of Mechanical Engineers described Sellers as inspired by Britain's adoption of Whitworth's comprehensive system. Later national and international standards continued the same negotiation. Profiles competed, dimensions were revised, and wartime production exposed the cost of incompatible systems. Standardization was a process, not a coronation. Formal recognition also came later than casual retellings imply. Whitworth proposed his system in 1841 and industry adopted it widely, but the British Engineering Standards Association formally adopted British Standard Whitworth in 1905. A standard can therefore exist socially before it exists bureaucratically. Railways, builders, and manufacturers made it real through repeated purchases and specifications. The official document consolidated a convention that workshops had already chosen because each additional user increased its usefulness. This is a network effect in iron. One workshop adopting the thread gained some internal order. Two cooperating workshops gained exchange. An entire industrial economy gained a market for compatible tools and parts. The geometry did not make engines more powerful directly. It made the ecosystem around engines less wasteful. Machines became easier to assemble, maintain, sell, and understand across distance. The small hinge was agreement about a ridge too small to notice from across a room. There was also a cultural change. Craft skill had often included the ability to reproduce a singular part. Standards did not abolish skill, machinists still had to cut, measure, and judge materials. But they relocated some knowledge from the individual object into a shared specification. A drawing could name a thread instead of describing a private solution. A supplier could manufacture before meeting the final machine. An inspector could reject a part by testing it against a gauge. Knowledge became transferable alongside metal. That principle surrounds us now. Camera mounts, pipe fittings, bicycles, furniture, cars, and factory equipment all rely on specified interfaces, though most no longer use classic Whitworth fasteners. When a bolt from a packet fits a nut made by another company, the miracle is not the screw itself. Ancient engineers knew screws. The miracle is coordinated sameness, rival organizations restraining their freedom to improvise so customers gain freedom to repair and combine. Standard dimensions turn anonymous parts into dependable promises. Whitworth's particular 55-degree form survives most visibly in legacy machinery and related British thread families, while metric and unified systems dominate many modern applications. That makes the original object easy to overlook. Successful infrastructure disappears into expectation. We notice standards when an adapter is missing, a foreign fitting refuses to mate, or an old machine demands a wrench no current shop stocks. Incompatibility briefly restores the 19th century world. The standard changed competition usefully. Manufacturers could still compete over material, price, precision, and design while leaving the mating surface predictable. Agreement did not erase innovation, it fenced off one area where novelty imposed costs on everyone else. Modern technology repeats this bargain in plugs, data formats, and connectors. The hard question is which layer should remain open to invention and which should become a stable public interface. Threads make the case especially clear because differences can be invisible. Two bolts may share a nominal diameter and still damage each other when forced together. Compatibility is not resemblance. It is conformance to specified relationships. As factories bought components rather than making everything under one roof, trust moved from familiarity with one craftsman toward confidence in drawings, gauges, and named standards. Whitworth's profile was one answer, not sacred geometry. Sellers's 60-degree form and later metric standards showed that several technical solutions could work. The achievement lay in making the choice measurable and repeatable. Once engineers could point to a specification, incompatibility stopped looking like nature and became a coordination failure institutions could solve. Shared threads also enabled specialization. A firm could focus on fasteners, another on engines, and a third on repairs because the connection between their products was settled in advance. Markets widened when buyers no longer needed every supplier to copy a private pattern. Inventories became more predictable, catalogs more meaningful, and remote orders less risky. None of these gains required a spectacular new engine. They came from reducing the negotiation hidden inside every joint. In that sense, the standard was productive infrastructure, a rule that let countless other inventions combine more cheaply. A common gauge made that trust portable. The dinner table connection, then, is not simply that Whitworth invented a screw. He proposed that British workshops surrender countless private screws for one shared language, and builders soon used that language in structures as ambitious as the Crystal Palace. A common nut helped make mass repair and modular construction ordinary. Every time an anonymous replacement bolt turns smoothly into place, it reenacts the 1841 insight: civilization can advance when everyone agrees on the precise angle of a tiny threaded groove.